So welcome to Physics STK 3155 and 4155. So there's a question here. Could you say it again? So the video will, is that what you're thinking of, right? Yeah, so that will be, you will all get a message. So this is in chemistry. It's auditorium 2 in chemistry. But everybody will get a notice of where the backup lecture hall is. So we are a little bit unlucky with the delay in audio visual equipment. So I hope you can forgive us for that. So this is beyond what I can do actually. Now, what I wanted to say a little bit about practicalities first. So we have, as you've probably seen, we have an official website for the university. And that's where you find basically all the links. So I am this guy here. This is me with a kind of funny name. You find the schedule, which you probably have looked up. And you know that if you look at these kind of activities, actually this comes up in Norwegian now. So there's still things lagging behind. So on the websites, you will often see information in English and Norwegian messed up. But you can subscribe to these activities. Are you familiar with that possibility? So that means that if you subscribe to that, you will get a message in case we change lecture hall or if there are changes. So that if we make changes to the schedule, you will get that if you subscribe to the activities. So that's a kind of pretty useful thing to subscribe to. So if you haven't used it, feel free to use it. And there you will find links to the weekly plans, what we are planning to do. You will find the information about where you find the lecture notes, etc., etc. And there's also a link to the Zoom link if you want to use that one. Okay, so that's the official website. And if you use that one, if you scroll down here, you will see these are all the additional features we have. We use Canvas for handling of exercises and projects. There's a Discord channel, if you like to use that one, where you can drop questions and you can have discussions among yourself and with us. We will try to answer as quickly as possible. Obviously the Zoom link, and then there's a weekly update. You will receive that one as an email as well. So there will be an email about the plans for next week. And there we will also point to videos and teaching material, which we will cover that specific week. Okay, any questions so far? So don't hesitate to ask questions, right? And then the teaching material is all on GitHub. So I'm just going to jump into GitHub so that you can actually take a look at that. So if you go to the GitHub site, this is the, it doesn't look that fancy, but this contains a link to the lecture notes, which we are going to use. It contains also links to, if you go into the doc folder here, you will find lots of material. So under the pub folder, you will find the material for every week. So if you click on week 34, there is an HTML version of the lecture notes, if you prefer to use that one. And then there's a Jupyter notebook. And I will often use the Jupyter notebook during the lecture, in addition to my whiteboard. So I typically take notes on my whiteboard, and that means that the PDF file, which I produce from that one, is something which you will also have access to after the lectures. So that's just like a regular whiteboard or blackboard note, set of notes, and I normally save them, and then you can always revisit them in case you were in doubt and if I went too fast, etc., etc. Okay, so that's the GitHub address. And how many of you, I should rather ask, since everybody is more or less familiar, is there somebody who's never used GitHub? Fantastic. So GitHub is not the only provider So Git is the version control software, and GitHub is one of the possible providers where you can save your files. You have GitLab, you have Bitbucket, and many other providers. I've been using GitHub, and the university has also the possibility to give you a GitHub account if you want to use that. Or if you prefer GitLab, I mean, use that. Now, the thing which is nice is that these lecture notes, you can simply, if you click on here, you can download them to your own laptop. Feel free to use them as you want, okay? So the kind of weekly material is something which I also update. I discover errors, typos, etc. So I will keep updating the material. And that means that if you refresh now and then, you will get the latest update with corrections, etc. Now, one of the things is that if you don't want my version, if you want to make changes yourself, what we normally recommend is to use the fork option. So that means that you save it as your own, and then you can make your own changes, etc., etc. So feel free to do that. And you can see there are something like 120 people who actually forked this one. And then you can use the notes as your own electronic notes. And if you like working with that, this becomes then your electronic lecture notes. So that's a little bit about the main site of where you find information. If you click on this site link here, there is a, just increase the fonts a little bit. If you scroll down, you will then find the different chapters. But then, if you go down here, you will find the weekly material. So in this Jupyter book, you will find the things which look like a regular textbook. But at the same time, at the bottom here, you will find the material which we will discuss every week. In addition, we have weekly exercises. I will come back to that. So the labs, actually just outside the door here, there's a room which is called Physics 434, and we will meet there on Tuesdays and Wednesdays. And we are going to be in groups, so because the capacity is something like 30, 35, and that means we will have 4 groups, one from 8 to 12, the other one from 12 to 4. The lab is open till 6, and the same on Wednesday. So you have to choose the group you want to be in. I'm going to say a little bit more about practicalities here. So what I'm going to do next is simply just to say a little bit more about the setup here and the overview of the first week. So this week, we will discuss linear regression and get a little bit started with exercises, in addition to all these practicalities. So we would like you, and I'm going to increase the fonts a little bit here so that you can see a little bit better. So how's the view in the back there? Is it okay? So as you can see here, we will have these sessions on Tuesdays and Wednesdays, and you should select your group. And we will often have some quick reminders of topics we need to cover. Many of these exercises are linked up with the projects. So that means that you can reuse the code you have for the exercises in the projects. So we have 3 projects which are graded. And I will say a little bit more about these projects. And the weekly exercises, if you hand them in, and for the weekly exercises, we will give you a pretty brief feedback, not very in-depth, but for the projects, you will get a detailed feedback because that's what is graded. But you should use the lab sessions because that's where things really happen. We will also use some of these sessions here for active learning. So sometimes I will just have a short recap of what we did the week before, and then we are going to work on exercises and projects. But then the lab sessions function really as the place where we do things. So try to find a group, and one of the things which we normally do is we ask you to form groups if you want to do that. Optimal working groups are 2 to 3 people. You can hand in just one project per group, and obviously you get the same grade then. It's very beneficial to work together because you can have somebody who is very good at programming, somebody who's good in mathematics. So this course is a mix of mathematics, linear algebra, optimization, statistics, programming, and then applications to specific systems. So if you're 2 to 3 people, you can really benefit from each other. And the third person could be somebody like me who is good at making coffee or cracking bad jokes. You need somebody like that as well, right? Anyway, so these are the group sessions on Tuesdays and Wednesdays. And I see that there is a question in, so sometimes I try to answer some of the questions. So when it comes to groups, this is a very good question because that's the next thing I wanted to say something about. So one thing you will get is an email where you just fill in a Google Docs about your background if you want to be in a group, because not everybody knows everybody, right? So some people already have potential teammates and others don't know anyone. So I will then try to, based on your background, I will try to suggest groups, if that is okay. So you will get an email with a link to a Google Docs. So if you fill in that one, then I will, by the end of the week, I will try to make suggestions of who could work as a team. It doesn't work always, but in most cases it actually seems to have function, okay? So you will get an email later today about how to, I mean, we just say something about your background, courses you've taken, etc. And then I will try to bring people together depending on the background. Perhaps sometimes there are people from the same study program, and then I will try to bring people from the same study program together. Okay. So the hope was obviously that this lecture hall was ready for the semester, but it is not, as you see. So it's we will you will also get a message on whether we move to this backup auditorium by the end of the week, because they may actually have to do some work here, which means that we cannot use the hall here. Okay. So this is roughly what I want to do. I give a presentation. Of course, linear regression is what we will begin with. I'm coming back to that. And then Mondays, we have regular lectures. So again, there's a little bit repeating here. So the weekly exercises, you can actually get an extra score on that. There's no final exam, as I said, there are 3 projects only. So we have a Discord channel, and then we also use Canvas. So Canvas is where I can access your email address. So all the emailing which I do is through Canvas. So if you haven't put a kind of a warning on Canvas, because sometimes the mail stays within Canvas, but you have an option there where you can actually say forward to my email address so that you actually get it in your mailbox. So we have 3 compulsory projects. And one of the things we'd like to do is that for the last, so the first project is about regression type of problems. So linear regression does not sound like machine learning. You can view linear regression, which we come to, as a kind of low-level machine learning. And it's a way to get started with many of the basic concepts because it links well with statistics, it has the optimization part, it has a lot of linear algebra, etc. And we have analytical expressions, which you can program. So the learning takes place through an analytical expression. So it's in every textbook on machine learning, you will often find that they start with a linear regression and so-called logistic regression, which I'm coming back to. So these are some of the basic startup ingredients. So think of that as a kind of low-level machine learning. And the second project is you writing a code for a neural network. So that would be the deep learning method. And then we will also cover other methods where you can use software like TensorFlow or PyTorch or existing libraries. So how many of you are familiar with a library called PyTorch? Okay, so many of you use that one. That's a pretty good library. And some of you may have used TensorFlow. Anyone who's used that? I see a lot of you. So these are typical library which you can use for the last project. And in the last project, you're actually free to choose the topic. Obviously, you should use the methods we have discussed, but the data set you want to analyze is something which we come with suggestions, but then people have their own data sets they would like to analyze, so that you can link this up to, let's say, your master thesis project or your PhD project, or if you just have some fun data you wanted to study. So we want this to be a kind of course where you have this freedom, and also you can link it up with your own, let's say, research topics or interests. That's the kind of idea. And for me as a teacher, this is extremely nice because I learn much more, and people do many, many fancy things. We had once a student from economy from Brazil, and she actually had data from the stock market in Sao Paulo, which she wanted to simulate. And that was a very interesting project. And there are many, many other such type of projects which people have done. So for me as a teacher, this is very, how to say, nice, because I learn much more myself. There's one thing which I wanted to say, and there's been a lot of kind of, so this is something we have to agree upon in the beginning of the semester, and it deals with the usage of AI in education. So things like ChatGPT or other types of tools. So the way we have done it here is that we want you to use these tools as much as you can, okay? But there are some constraints. Now, you're going to write scientific projects. So the projects are going to look like a scientific report. So that is also part of the training here. So how many of you have written scientific reports? Okay, not everybody. So you can view this as a kind of the training, which can prepare you and help you for, let's say, thesis work. A master thesis is essentially a technical report, a scientific report, with essentially the same structure. Now, many of you are not English speakers, which means that to write an introduction sometimes can be difficult. So the way you could do that is to actually write in ChatGPT, for instance, on a prompt, give me inspiration for writing about linear regression. And then you know that every time you ask, you get different questions, answers, right? So if you use these tools to, let's say, get ideas for the introduction or other parts of the text, then you should include in the report at the end or on your GitHub site a link to the ChatGPT conversation, because then we can see how you used it. So if you used it, you should state it, okay? But feel free to use it because it's a very good aid. Now, we do have people who cannot be here, and that means that they don't have the possibility to ask us whenever it fits. And then ChatGPT or similar software is like a body you can ask scientific questions to. So use that as a tool, because it's not always that you can be here, or it's not always that you find one of us. So this is an extremely useful tool, and you should use it, but with care, because sometimes you get answers which are just garbage. So we had an example last year of somebody who actually used ChatGPT to write introduction, and the introduction didn't make sense. So then what we typically do then is that we come back with feedback and say, don't do this next time. So many of you have probably been a little bit scared about these discussions about what is legal and not, cheating, etc. So we take a very flexible approach to it, and we simply rely on your honesty, okay? But if you use these tools, then we would like to see the conversation you have. Because like writing an introduction, many of you have never written an introduction about, let's say, neural networks. And how do I start writing it? So you can get inspiration from this. So keep also in mind, and this is a kind of, how to say, this is my, so when I write a scientific paper, I actually spend a week at least on the introduction. And what I typically do then is that I read many, many other scientific papers. So I don't use ChatGPT, but I read these papers because that gives me an update of what other people have done. And then you can put things in the right context. So obviously you lose that part in your own development of your insights about a problem. So try to use these tools as what they are, tools. Sometimes they give you just garbage. So it requires that you have a kind of deeper insight about what it gives you. Okay, any questions? Was that, yeah? I have to take this off because this has a kind of, yeah. Oh yeah, please. Yeah. So, yeah, you can, exactly. You can do the same way. But you would have to state it that you used it. So as long as you state, because one of the things you have to put in the report is a list of references, and there it would be natural to put, I used Google Copilot, for instance. So these are tools which make life easier, and use them as they are, okay? If you are in doubt, the lab sessions are the best places to discuss these things, okay? So I wanted to use a little bit time on this because many people are uncertain on how can I use them? And will people accuse me of cheating? So the way we will do it is that in the first project, we will give you feedback so that you can actually correct this later. Okay. Yeah, we use Python as a default. Here we have a list of teachers. In my case, just use my text. I didn't put the additional information about the TAs because they are students like you. So they may be busy with courses and other things, but they will be at the lab, obviously. So the deadlines here are tentative. So these deadlines are for your planning of the semester. And just take a note of that. You will find that in the Jupyter notebook or in the weekly material. So this is what we are kind of aiming on, October 7th, November 4th, and December 9th. And you can get an extra credit based on the weekly exercises. So there are 10 weekly exercises, and that means that you can get 10 additional points. So how can these be converted into a grade? So if you look at the grade scale, this is the way we grade. So suppose you have 88 points on the 3 projects. And then you've handed in all the weekly exercises. Then you get 10 additional points. So then you end up with 98 points. So even if your projects corresponded to a B, if you did the weekly exercises, which we align with the projects, so it means that the weekly exercises are made so that they link with the projects. So we are actually baby stepping you through what you need to program. Then you can actually get an additional score. It's not mandatory, but if you do it, you will get an additional score. And as I said, feedback there will be sloppy, okay? Not very detailed. It's like thumbs up, well done, but not so much more, okay? This is simply because it takes a lot of time to give feedback. So giving feedback on a project is actually something which the TAs and myself as well, it's a kind of, it takes time. So please use the feedback. And you can, at the lab session, you can always ask us, what did I do wrong here? So this is actually, the lab session is really where things do happen. Okay. There's another question in the chat here. So the weekly assignments can also be done by groups. So there's a question in the chat here whether the weekly assignments are individual or group assignments. So if you collaborate as a group, you can also upload as a group the weekly assignment. Now, do one thing, however, because sometimes Canvas doesn't take a group. So if you are a group composed of 3 people, to be safe, everyone should upload the weekly assignment and the projects. So sometimes it has actually failed, even if we say that this is a group assignment, it has actually failed and it has only listed one of the members. So do actually upload individually, but you can have the same answer as the other 2. We've also had groups where people have collaborated on writing the project and discussing, etc., etc., but they ended up writing their own individual projects. So this is up to the group, how you decide to write the project, either as one unique hand-in or that people choose to write their own story. Yes, all 3 reports contribute equally to the final grade. So there are 2 textbooks which I'm going to use. One is actually the kind of standard textbook on deep learning. You can access that for free, chapter by chapter. This is the book by Benjo, Goodfellow, and what's the name of the other author? That's Goodfellow and Coville. This is a kind of textbook which, how to say, it contains a lot of details, but it doesn't contain any codes, unfortunately. So many of these textbooks on machine learning, they are either very mathematical or they are kind of mathematical and lots of discussions. This is the case with that book. And they contain no code, or they contain code and a very shallow discussion of the mathematics. So I haven't found a textbook which really fits everything. The one by Benjo, etc., you can actually download chapter by chapter, and I will send you weekly reading suggestions based on that book. And also, the one by Sebastian Raschka contains lots of Python codes. And that's the kind of hands-on book. And I will also refer to that one. You can go to the Jupyter address of the author. Every chapter is actually a Jupyter notebook. So you can access that for almost free. It doesn't contain all the text, but you can also buy the text. It's actually not very expensive. And it's a book which I would recommend quite a lot, the one by Raschka. It contains lots of this kind of tricks of the trade. And we are going to refer to different parts of that book as we move on in the semester. But the Jupyter notebooks are very, very handy. And it has a very nice chapter on using PyTorch as programming environment. So TensorFlow is a library for machine learning, and that was released by Google in 2015. PyTorch is Facebook equivalent. And then we have another library which we will be using, which is called scikit-learn. So these are 3 of the most, famous machine learning libraries. Any questions so far? Yeah? I haven't done that. So actually, in the beginning, we would like you to write more codes yourself so that you get a little bit more familiar what goes on behind the curtain. And then in the final project, you should just use the library as they are, because it will take you much more time to write a code for convolutional neural network. We have an advanced course on this, and then typically a project is to write a code for the whole semester. So in the 3rd project, we normally tell people use existing libraries. Obviously, you should try to cover and use the methods we have discussed, because else, I mean, it wouldn't be relevant for the course, right? So you will also find in the GitHub address, and that should be here. So if you go back to the GitHub address, there is a link to something which is called textbooks. And surprise, there are PDF versions of books. I don't know how they happen to be there. They just ended up there. But that contains a PDF. So actually, if you search online, you will find many of these textbooks, PDF files. Now, there's another thing you should be aware of, is that the university here, when they buy journals and textbooks, you have free access to the PDF file of textbooks. So publishers like Cambridge, Oxford, Springer, Elsevier, and so on, the textbooks which are published by them are freely accessible to you if you go to the library website. Are you familiar with that? So you will see that some of the textbooks here, they're actually taken from Springer's websites. Some are taken from Cambridge, Oxford, which are famous publishers. So basically all the big publishers, they provide through the university links, because we pay for that. There's a bundle, you pay for the journals, for the textbooks, etc. So you have free access to these. Okay, let's go back to the Jupyter Notebook. So there's a long list here. You can just look these up things. And what I would say here, we need to refresh some linear algebra. And we will discuss that more also tomorrow and on Wednesday during the lab sessions. And I will actually bring this up on my whiteboard as well today. So these are some prerequisites. I'm going to go quickly through some of these things because these are things you can read yourself, if that is okay. Just stop me. There's a little bit about the machine learning, the type of things we will go through. And as I said, these are some of the methods which we will discuss. And we will start with linear regression and logistic regression, because that also allows us to discuss the optimization part. And then we are going to look at the decision trees, support vector machines, and we'll also say, if you have time, something about some unsupervised learning. So I need to say a little bit about the type of learning we will cover. So the two typical types of learning are supervised, which in Norwegian is leder, læring, and unsupervised. So supervised means that you have labeled the data. That is the most common situation. So you have labeled the data. You can have labeled the data for paintings, and you could say that this is a Van Gogh painting, this is not a Van Gogh, and then you put a label 1 and 0, yes, no, and then you can train a model on that, so that you can feed an image of another painting, and then you can ask your machine learning algorithm, which you have trained, to recognize whether this is a Van Gogh or not. So this is a very standard situation, labeled data. Now, labeled data is a situation which is very expensive because it means that somebody has actually done it. So I don't know how familiar you are with some of these face recognition algorithms. There have been projects about from your facial expression, whether one could predict what you would do. There was a big project by the American Defense Department to actually be able to predict from facial expressions whether you would commit a crime or not. This is actually pretty shady research, and it was abandoned. But you had tons of people then who would classify facial expressions. And clearly this is also dependent on where you are in the world, right? Because facial expressions may have different meanings. So some of the models are actually trained with quite some bias. And it means that the training part itself with labeled data is something which can be very expensive. It can have a bias, but it's normally the kind of standard situation. If you run an experiment, you will often label whether this is a specific outcome or not. The most typical situation for classification, this is another type of machine learning situation. You want to classify whether this is a specific event or not. Yes, no, 1, 0. This is a binary case. This is one of the most common classification problems. So classification is a typical supervised learning problem, but it can also be unsupervised. So unsupervised means that you just give a set of data and you want the algorithm to figure out what this data represents. And that is a more common situation in many sciences and disciplines, because you don't have the possibility to label all the data. So clearly, if you have to pay people to label the data, it becomes expensive and time consuming. So supervised learning, unsupervised learning are the cases we will discuss. And then we are going to look at the classification. We are going to look at the regression, which means essentially that you want to fit a function to some data. That is a very common case. So you can have an output from an experiment and you want to fit a polynomial to that data set. And this is where we are going to begin this semester, with a typical polynomial fitting case or a regression type of problem. Okay? So the deep learning methods which we will end up with are those which you see here. We will essentially cover neural networks and convolutional networks and recurrent neural networks. We will discuss those. So for neural networks, you will actually write your own code. Whereas for convolutional neural networks and recurrent ones, we will use PyTorch and TensorFlow and show you how you can use that. But we are going to go through the mathematics of these methods. These are the tools which we normally recommend. So for many of you, I should rather say, is there anyone who has not used Python as a programming language? Okay. Basically, everybody's familiar with Python. Good. If you're not, we're going to team you up in a group where you can benefit from the other people. And you will see lots of examples in the lecture notes on how to use Python. And one thing which we normally recommend, if you're not too familiar with using terminal mode, is actually to use some kind of integrated development environment or an IDE, and Anaconda is one of these. And you're probably familiar with that. So how many of you have used Anaconda? Oh, good. Also, every year, there's somebody who wants to write code in Julia. Anyone who would like to do that? Yeah. So Carl Hendrik, who is one of the TAs, will be very happy with that. You've probably seen from my age that I most likely have also programmed in Fortran. So if there's somebody who wants, we've had people who wrote everything from scratch in Fortran or C++. Anyone who wants to do that? That takes much more time, right? Yeah, we can use Fortran or C++ if you want to, but it will take you more time because many of the libraries nowadays are tuned to Python and Julia. But there are machine learning libraries in C++ as well. So that's also another possibility. And we have people at the lab who can help you with these things. So we want to give you this kind of flexibility, but you have to strike a balance between how much time you want to use and how much time you have at your disposal. So there's a long list here of other courses. So we have an advanced one on machine learning for the physical sciences, which is in the spring. We have the natural language processing, which is pretty close to this course as well. Many people like to take this course, STK IN4300, because that has it goes more in depth with the mathematics. There's less programming. So this course is a mix between the mathematics of machine learning, programming, and obviously applications to a specific data set. So that course has a more emphasis on the statistical interpretation of the results. So for those of you who are interested in that, this is a very good companion course with this one, because there's a limit to how much we can cover. So feel free to look at that one. Now, in the spring semester, there is actually a course on deep learning for image analysis. So that's one of the really hot applications of deep learning methods. And that is called IN 4310, which is also a very nice course. And then there are courses on computational statistics, Bayesian analysis, etc., etc. Now, there's one thing I wanted to say about the content of this course. So we are going to scratch the surface of a statistical analysis, but we are going to stay in what you might call a traditional machine learning approach. So what does that mean? Now, that means that we will focus on fitting data and have a model which then learns from the data, and you can use that one to make predictions. It means you can find correlations in the data set, and you can make predictions. That is the standard machine learning approach. And for those of you who are familiar with statistics, this normally falls within a slot which is called frequentist statistics. We are less interested in the probability distribution. That's why I mentioned this other course, statistical learning methods, because that includes also what is called Bayesian approach to machine learning. So is anyone familiar with Bayes' theorem? Who has heard of Bayes' theorem? So Bayes' theorem is the same as, is in statistics, the same as Pythagoras in geometry. It's a fundamental theorem. And it's used in machine learning as well. So instead of fitting a function, we try to extract a probability distribution. With a probability distribution, you can make predictions, you can find correlations in the data, but you can also find an estimate of the error of your parameters, which is extremely useful because then you can tell your friends that this model has this and this uncertainty. So I make a prediction with this and this confidence. And that's extremely useful. In addition, with a probability distribution, you have something which is called causation or orsakssammenheng. So you can predict what is the probability of A given B. In the standard machine learning approach, this has not been the case. So we will stay more with the standard machine learning approach, but we are going to bring in elements from statistics as well. And linear regression is one of the cases which lends itself to a very nice statistical interpretation. So Gauss, when he developed linear regression almost 200 years ago, it's actually intimidating when you see what Gauss actually did. The name pops up everywhere: linear algebra, integration, derivation, etc., etc. But Gauss developed both the linear algebra approach, which we will start with, but then also a statistical derivation of linear regression, which is one of these low-level methods. And one of the reasons why we start with linear regression is actually because of that, because it allows us to catch many birds with just one stone. Okay, any questions so far? Too much blah blah from my side, eh? Okay, so we should also take breaks if that is okay with you guys. I think it's time to stop now, have a small break. Feel free to ask questions. You probably have tons of questions. And then I would just suggest that we stay here, the next lecture. And then if there's going to be work here in the coming days, we will move to the backup room next week. Okay, so let's just stop the recording, put it on pause. Now, feel free to ask questions or stretch legs or do whatever you want. Yeah. Så dette med som så det Gjennom selvbildet, så skal jeg sende videre til studenten. De tingene der. Ja. Ja. Det var her som ikke ble ferdig. Ja, ok. Det skal være fullt om. Ikke tenkte vi. Ja. Oh, no. No. There's nothing mandatory here, except the 3 projects.
Okay, yeah. So this information because I was
Yeah.
unable.
So if you go to the web page of the course, I mean the official one, you just go to that one, just the official website, and then there are links there for all the information. So you would just punch in FYS-STK. Oh, but no, you don't need to log in actually. You can just search it in the browser. Yeah, that one. And if you then look at this semester, the autumn, that one, click on that one, and then you go down, and then you have down here, you have all the links to the information. And that's where you find the GitHub site, which I linked to, the weekly material, and then the Jupyter book. So everything is there. You can use the notes as you want. You can download it and then treat them as your own notes. Yeah.
So much scared.
No, don't be that, because we are going to put people together. So if you want to work in a group, as I said, I'm going to send an email about the Google Docs where you can just state, I would like to collaborate with somebody. You give me your email address, your name, and then your background. And then I try to bring people together, because this course is taken by people from essentially all departments in the College of Natural Science. There are people from medicine, there are people from economy, across the whole university.
Geology.
From geology. So what I would do then is actually just to try to set the groups together, and just as a suggestion, that to team up people, 2 to 3 people. And then, so that means you will get an email by the end of the week or during the weekend with suggestions. And what else? We have it could happen that you meet other people from geology because during the group sessions, then maybe you reckon some faces and you've seen before, and then you can just ask them, would you like to collaborate? Yeah, well, that's up to you. And some people want to just work alone. So there's no, being a group is always an advantage because you learn much more. Unless you're extremely confident and you know everything. Okay, thanks. No, it's my pleasure. Eh? Ja. Det er ingenting, så. De har ikke satt opp noe som helst. Nei, jeg vet det. Det er sunt. De har faktisk, når de har gjort dette rommet her, så har de ikke tenkt at... Nei, jeg beklager, altså, den... Ja. LM. Ja. Bør man ha den? Bør man kjøpe den? Tenker du på den til... Ja, skal vi se, bare vent litt grann. Bare vent litt, skal bare ta den... Unnskyld. Der. Skal vi se. Jeg har tatt den til... Du tenker på den til Rashka, sant? Den, ja. Ja. Ja, altså den henter du på nettet, altså kapitlet. Og her ligger Jupyter-notebookene på websiden hans. Så der kan du laste ned alle Jupyter-notebookene til hvert kapittel. Til han? Ja, til han i Rashka, ja. Ok, hvor ligger den da? Så hvis du søker på, hvis du går på den Sebastian Rashka her, på den lenka der. Ja, men det er også lenke til ja, det skal være det, altså. Den skal vi se nå. GitHub. Så den har, hvis du søker bare på den, så har du med en gang, der skal det være lenke til den boka hans, så du har maskinlearning-bok, den. Jeg tror det er denne, enten, ja, så jeg vil gå til den altså. Ja, og der finner du alle Jupyter-notebookene hans. Skal vi se, jeg skal bare stoppe den. Ja, du hadde også et spørsmål?
Et litt spørsmål.
Ja.
Der du ikke får se hele labben. Jeg ser jeg har en labb som krasjer.
Nei, men det går fint. Det går fint, det. Det er fint.
Så,
Ja da, det går fint det altså. Skal vi se. Ja, ser den, ja.
hvordan fungerer sign-up for gruppen?
Du har egentlig hatt mulighet til å melde deg på dem.
Ja.
Men så, det vi stort sett har gjort, at folk har, hvis de ikke har passet helt, så har de bare møtt opp på den gruppa passet, så ser de om det er plass.
Fordi at den gruppen jeg fikk til, har jeg forelesning.
Ja, nettopp. Så prøv bare å følge frem litt og se om det passer.
Ja.
Og hvis det er plass der, fordi det er typisk, det rommet der har en kapasitet på 30-35.
Ja.
Så det er som regel godt bra. Vi prøver å fikse det. Det går fint det. For those of you online, can you hear me now again? Because I'm going to put on the recording pretty soon. So if you hear me well, excellent, excellent. Okay, is it okay if we start again? I'm going to put on the recording again. So. Okay, so let's get started again. And I just wanted to start with the basic mathematics. So I'm going to switch pretty soon to the whiteboard. And I hope you still can see well the screen. It's not an optimal setup, as I said. So what we are going to get started with is to look at some simpler cases. And the exercises which we have this week and next week are implementations of these cases. We will also discuss some of it during the lab session tomorrow and on Wednesday. So every lab session is identical, which means that there may be a short session, half an hour at most in the beginning, where we present some details which are needed for solving the exercises and for the project, recap things. And then we move on to the weekly assignments and or the project itself. So the first ingredient when we do machine learning is our data set. So that could typically be you having made a measurement of a position of a car. So you have a position X and you measure the velocity, for instance. Or you measure the position as a function of time. That's a very simple measurement. Even I can do that. And then time would be your input, and then the output is a position, right? So that's a simple measurement, and that would be your data. And then you would like to make a fit. So that means that the second item in machine learning is the model. So if you're assuming that the car drives at a constant speed, then you know exactly what kind of model you should use, just a constant. If you know it to accelerate, you may fit it with another model. So this is the second ingredient. Then you have a third ingredient, which is normally called a cost loss. It has many names depending on the field. If you go into finance, it's called risk function. I like often the error function. This is a function which allows you to gauge the quality of your model. So you have the input data, output data, that's the data set. You have a model which you make, and then you want to assess if this is a good model or not. And the way you assess that is by some mathematical function. So if I give you a model and the data, and I train a model, and you're now looking at data which are continuous, what kind of function would you use? Could you use? There are many functions. What strikes you as a simple function to assess the quality of the model towards the data you have? Any good suggestions? There's a mathematical function which you probably have seen. Actually, there are several ones. So if you have a model, and then you want to measure the difference between the model and the data, what strikes you as a simple function to do that? Any good suggestions? Yeah? Mean squared value. That's one thing. So you take the difference between your data points and the model you have made, and you square it, and you sum it up. That will put an emphasis on large deviations, right? If you have a large deviation, you square it, then clearly that will become, if you have deviations for large values, then you will get a large mean squared error. You have other possibilities. So the mean squared error is one. We are going back to that on the whiteboard pretty soon. Any other simple functions? So yeah, any norm. You can take the relative error or the absolute error. So you can actually choose any norm. The choice of norm has consequences when it comes to the optimization problem. So we've said now we have 3 ingredients: the data set, the model which you make. This model doesn't need to be a polynomial, but it could be a probability distribution if you want to fit that. So if you're doing Bayesian statistics, then you would be fitting a probability distribution. And then we have this function which we have to cook up. So this is something which can have its pros and cons. And when you look up in the literature, you will find tons of functions which you use to gauge the quality of your model. And some of them are going to give us analytical expressions which are easy to implement when it comes to training a model. And the mean squared error is one of these. So when you've done that, at the heart of all of machine learning, there is an optimization part. So that means that what we are essentially going to do now as our first warm-up case is actually to take the gradient of the mean squared error. And then we want to drive this gradient to 0. And that will give us an expression for the unknown parameters of the model. That is the training. So in this particular case with linear regression, which many of you probably have seen as least squares method back in linear algebra, does that ring a bell? So that's something which you often encounter when you take a course in linear algebra. And this is what Gauss did back in 1850 and so on. By the way, do you know the story about the Gaussian distribution? There's a kind of legend behind it. Now, At many of these universities in the 18th century, 19th century, many of the professors, they tended to marry much younger women. So the university was very worried with pension obligations because they knew that the wife, which could be 30 years younger, would outlive this old male professor, right? And the university felt its pension fund would go bankruptcy. So what Gauss did then was actually to look at the age distribution. And then he found the Gaussian curve. That's the kind of legend behind the Gaussian curve and the Gaussian distribution. And then he could go back to the university and say that there's most likely not going to be a problem with the pensions. Just look at these age distribution curves. So that was a kind of legend. I don't know if it's true. I think it's fun. Maybe it's not that fun. Okay, so let's switch to the whiteboard, and let's get a bit started. So I'm not going to go through some of these examples here because, oh yeah, maybe I should say a little bit. There are, before we move on to the whiteboard, there are some libraries which we recommend. So I guess you're all familiar with NumPy. So how many of you have used pandas? Quite a lot. How many of you know that there is something which is called Pandas AI? Have you heard of that? Use it. So Pandas is a very efficient way to read in data. With Pandas AI, you can just write on the text line, write me a code which reads the data in this format. That simplifies, because when you've done the reading of data once or twice, you've written your code, there is not much new insight in writing a new code for reading data. So, but preparing the data is something which is often sometimes the most time-consuming part. So for some master projects, it can actually be 80% of the time you spend on reading in data and setting up the data for specific algorithm. In this course, we are not going to spend much time on it, but we are going to look at pre-processing of data, which is important. So we will scale data and we'll also pre-process it so that we can reduce the type of errors which come from outliers. So this is something we come back to. But we will not put that much emphasis on, preparing a data set. On the other hand, we had a project some 3-4 years ago of a group of 5 people where they had data from oil wells. And that data was not treated properly for machine learning algorithms, but the group consisted of people from computer science who were experts on massaging the data in the right format, one who knew the meaning of the data, and then there was one mathematics student who was an expert on specific algorithms. So that group really worked well, and they made an excellent project, which ended up as a scientific publication. So we've had cases here. This is not a requirement, obviously, but we had cases where the projects have ended up in scientific publications. So these are tools which we recommend strongly. So there is one tool which you will find extremely useful. Have you heard of automatic differentiation? So who has anyone heard of it? One person has heard. This is actually a project which dates back to the 70s, and it's just essential. And it's what saves the day, especially when you have complicated functions you want to take the derivatives of. So automatic differentiation is a big mathematical project, and this is reflected in software which is called AutoGrad, which allows you, we will come back to this, and when you're writing a code for neural network, you will find this extremely useful. So this is another type of algorithm which we will discuss in the optimization part. So AutoGrad, but then JAX has actually replaced AutoGrad. So JAX includes also just-in-time compilation and the AutoGrad project. So these are 2 kind of tools, or automatic differentiation is an indispensable tool in machine learning, in particular in deep learning methods. And that gives you a lot of flexibility when you program, because it means that you can change the function you want to optimize without having to hard code the derivatives of that function. So automatic differentiation does it. So what it does is actually to use the chain rule, and then the chain rule on you splitting up everything in simple mathematical functions. So many of the functions you actually have, they are cosine, sines, and simpler functions. And then you can use the chain rule for derivatives. So automatic differentiation, if you take a function like the exponential, e of x, has any of you, is some of you familiar with the finite difference method for derivatives? That is the standard methods, which you will encounter in all codes for solving, for instance, partial differential equations. That takes a difference between two numbers, right? If you use Euler's method to calculate the derivative, that suffers from numerical inaccuracies. If you use automatic differentiation, you can actually get the derivative or higher derivatives of the exponential function to numerical precision. If you use finite difference, you will fail dramatically, even for such a simple function. So automatic differentiation is one of these algorithms we will cover in more depth, and it becomes essential when we deal with deep learning methods. So these are tools and softwares which are very important. We have SymPy, scikit-learn is one of the libraries we will use. So scikit-learn does not have advanced deep learning libraries, but it contains many of the standard methods, and it has a lot of auxiliary functions for really massaging the data in the right format. And you are going to see how you can use that in an efficient way, so you don't have to write extensive codes. And then we have TensorFlow and PyTorch, and we will focus more on TensorFlow and PyTorch with more emphasis on PyTorch. So there are some examples here, and I will come back to these in the lab session tomorrow. But I wanted to jump to, so there's a reminder of NumPy. You can take a look at these things and run them just to refresh some linear algebra. But we will then bring this up a little bit later. There are examples on how to use pandas, and I recommend take a look at pandas AI. But I wanted to scroll down a little bit and go into more the theory and say a little bit more. So these examples are things which I will discuss during the lab session tomorrow. And then I wanted to jump more into the theory. So if we go down a little bit, the question is, why do we typically start with linear regression? So linear regression is a simpler method to get started with, and it has many pedagogical aspects. And hopefully that will allow you to see the wood for the trees and make it a little bit easier to get started with many of the machine learning applications. So it's normally a method of choice of fitting a continuous functions. It contains, as I said, it's a kind of low-level machine learning, but it has many features with understandable pedagogical links to other methods. It gives you an analytical expression for the parameters, the unknown parameters, and it has also the possibility to give you analytical expression for statistical properties. You can derive it from a Gaussian distribution, and we will do that. So you can link it with a Bayesian approach. It's easy to introduce some essential concepts, which is like the bias variance trade-off. Has any one of you heard about that? Bias variance trade-off? Does that say anything? So these are one of the things we will discuss, which is one of the tests of the quality of your model. Because you can have tons of parameters, and that can lead to overfitting. And then the question is, when do I overfit? Are there ways to understand when you overfit? Because clearly, if you overfit, you will often just get garbage out. And you want to avoid that. And you want to avoid underfitting. So you want to have a model which does an ideal fit of the data. So there are many things here which are easy to introduce. It's easy to code. And it also allows an easy understanding of gradient methods. So gradient methods is a common denominator for the optimization part. So I said there are three main parts: the data set, the model you make, the function you use to gauge the quality of the model, and then there is an optimization part. So how many of you have studied optimization theory? Yeah, some of you. So how many of you have heard of gradient descent methods? Okay, there's more of you. So that's part of this optimization theory. And gradient methods play an essential role in machine learning in the optimization of a given model. And the problem we often face is that we have models with tons of parameters. So the surface you want to optimize and find the minimum of is a multidimensional beast. And then the thing is, how do we reliably assess whether we are at a minimum or a maximum? These may not even exist. So what I'm going to do now is actually to switch to the whiteboard. So let's do that quickly. Can everybody see properly here? Is it okay? So I'm just going to sit down here now and try to see if my pen works properly. So if we now start with linear regression, which is going to, oops. So I've been having some problems with my pen lately. Let me just do one small thing here. Right? I need to do that one. So too many technical problems, guys. Let me see now. Okay, well, that should be going. Okay, so if we now start with linear regression, and what we have is a data set. So this is the first element. And we are going to make it a little bit easy for ourselves. So we could now think that we have some input data. And I'm just going to call this as a vector, X transpose. So I'm introducing some linear algebra notation already. And this is a vector now with I'm having some problems here. Right? If I'm having too many problems, I'm actually going to go back to my lecture notes. But we have now a data set here with some x0, x1, up to some xn minus 1. So this x here is a vector which we assume to be composed of reals of length n. So this could be like the time we are measuring when we measure the position of a car. So at a given time, x0, we measure position y0. So that means that we have an, I'm sorry guys, I mean, I'm having problems with my pen. And that didn't happen before right now. No, I have to switch back to my lecture notes here. I'm sorry for that. It seems that my pen is not working properly. So let's go back to the lecture notes. So I hope you can survive that. So my pen actually failed. So today is not my day. But everything is also in the lecture notes here. Now, one of the things which we are going to start with is a set of data. So we can think of this X as the input to the data set. And we have a set of observations. And then we have the response. So that means that there's going to be a set of y of x, which is then going to be a similar vector of same length. We're assuming that this contains real numbers. And then we are going to set up a so-called matrix. So if you now look at these features which you have here, these x's. So think of this as something like just you're making a specific measurement, or alternatively, each x here could represent a specific feature. What does that mean? Suppose I look at housing prices. Then this x, which you see here, can be transformed into a matrix. So each n could be a given house. And then each column then could represent some feature of the house. And the feature of the house could be the number of rooms, the number of bathrooms, the size of the house, the price of the house, etc. So you can actually define each one of these, as you can see down here. We have an x of I, which now contains some specific feature, like house 1 has 10 rooms, house 2 has 3 rooms, etc. Alternatively, you could think of this as cancer data. So you have n patients, and then you could have a matrix where each column represents a specific feature, like the size of the tumor, the thickness of the tumor, the radius of the tumor, etc. So you can actually, you're not limited to just have an object X, the input data, which is a quantity which measures, for instance, only time or the position. Okay? So that means we can turn this into a matrix. And that matrix is actually an important quantity in all of machine learning. So you can now think of having something which has P features. If you're thinking of cancer data as an example, each feature could be a property of the tumor. Like I said, it could be the surface, could be the thickness, could be the color, etc., etc. And then you have n patients where you have obtained this information from. And that means that you can code this as a matrix, and that matrix is normally called the design matrix, or the feature matrix, or the characteristic matrix. We will normally call this for the design matrix. This is a matrix which contains your input data. This is your data, okay? So you have some specific inputs, and then this Y, which you see here, this Y here, that is something which we want to parameterize in some specific way. So the Y is your observation. So you could then say that for this cancer data, you could have an output which is a benign tumor or a malignant tumor. 1, 0, true, false. So this is a typical case of a classification problem where you have some input data which classify the tumor. You have the output, whether this is a good tumor or a bad tumor. And then you want to train a model which you then can use on data which was not included in the training. Actually, this is a very hot research field, and some of you may actually end up in medical applications of machine learning. Countries like China, you probably heard of the company Alibaba. Is that, you've heard of that? It's the equivalent of Google in China. They have invested billions on this type of machine learning, because China is a country which has a density of medical doctors which is not very high. And that means that when you look at a screening of tumors, it takes often the experts 1 to 2 days to analyze the data. So then you want to train an algorithm which recognizes easily the known or the good ones contra the bad ones. And then you have the suspicious cases, which you leave to the expert, a pathologist, which then can go through the more dubious cases. And that really saves time. And it's widely used in medicine. And you will see actually this as one of the more important applications of machine learning in these sciences. Now, we are doing regression, so we want to fit a function. So I am going to assume that there is a parameter beta, which is the unknown parameter. And one way to see that, and I'm going to skip this example, but we are going to look at a simple problem of linear models and linear algebra. So we are assuming that we have this set of output data, and then we have some input data, and then we have a relation between this, and we want to find a function which approximates this data. So one function which we could think of, the simplest one, is a polynomial. That makes sense? Everybody's met polynomials, right? So that means that these betas here are the unknown coefficients. This y tilde is my model. That's the one I want to assess the quality of. So y tilde here, and you will see that in the notes, I'm going to use that as a model here. Now, there's a very important assumption when we are dealing with many of these machine learning methods. And here we are making an assumption that there actually exists a continuous function which represents our data y. So this y tilde is meant to be an approximation to this function, which we don't know. And this epsilon, which you see here, is some kind of noise. So there may be noise and there may be not noise. The standard assumption in linear regression is that this noise is given by a normal distribution. Normal distribution means a Gaussian with zero mean value. So it's centered around zero, and it has a standard deviation. Does that sound okay? I'm going to fix my pen for tomorrow when we go back here, because sorry for that. But the assumption now is that this y tilde, there is actually an exact function which represents the data in this specific way. So we have a function f of x, which we don't know, which then represents this y tilde is meant to represent. And this is a standard polynomial approximation, right? So when we do that, we can rewrite everything as a linear algebra problem. So this is my observation, right? Y0, Y1, all these are the observations. Now I'm forcing this to be equal, but it is not, we know that. So actually we are making an approximation with a polynomial to a given degree. So you would now see this is x0, this is the input which we had to the power of 1, power of 2. This represents the intercept of a line. So if we have a straight line, then beta 2 up to beta n minus 1 are 0. And then we have only beta 1, that's a straight line, plus beta 0, and beta 0 is the intercept. And then we are making a fit of these functions, unknown parameters, so that we can reproduce all these outputs. I guess you've seen this before, right? So I'm just spelling it out, and now you see that when you spell it out like this, then we can rephrase this as a linear algebra problem rather quickly. I also want you to link this with what we call the feature matrix. Because what you have here can be rewritten as a matrix times a vector. So these betas will represent a vector which are unknown quantities. The x's are known, the y's are known. And we have a model for this noise, and we normally leave that out in the fitting. So every line here is going to be a row in a matrix, and every column or every power of n-1, n-2, etc., is going to be a column in a matrix, this design matrix. So you could then say that when we come back to these features, this will be the feature of x to the power of n-1. This will be the feature of x to the power of 2, etc., etc. So you can then rewrite this problem as a plain linear algebra problem. So where we define this vector, the unknown quantities, we have this quantity here, which we actually don't include in the fitting. And then we have this design matrix. So what I'm going to do now, if you just look back at us writing out every line by line, everything we have, then we have a matrix, now vector y with the known quantities. These are the outputs. We have the betas, and then we have this design matrix. So every row represents one of the input data, x, and every column represents a feature. If you're looking at cancer data, you would obviously not have this model because the ones are just the intercept. But if you look at this cancer data I mentioned, then x0 could be the thickness of the tumor, x1 could be the radius, x2 could be the quantity like, no, sorry, not x2. Actually, this column could be the thickness. This column could represent the radius. And all the other columns would then typically represent a given feature of a tumor. In this specific case, we have put in as many parameters as we have data points. That is normally not the case. And that matrix has a special name in linear algebra. Has any one of you encountered this matrix? Now, it's called a van der Monde matrix. So if you cook up a special matrix, you can actually, and nobody has done it before, maybe you can have a matrix with your name on it. But that is a matrix which now is quadratic. So it's an n times n matrix. But normally, the number of columns which represent the features is much smaller than the number of data. So some popular data set on cancer, they have 10,000 patients and 30, 40 features. So that would be a matrix of 10,000 times 40. So in this specific case, the matrix is now given by a square matrix, but that's not normally the case. Now, the next thing you can do now, you can rewrite your equation like this. So I have a matrix which is given by this design matrix, and I have the unknown parameters beta. And this function, x times beta, is going to be my function I'm going to fit, the y tilde. So ideally, there is, and I said there is an assumption here that x times beta is going to represent an exact function which we don't know. So we make an assumption that there is a function f of x, which is continuous, which exists, but we don't know it. So what you see here, this x design matrix multiplied with the unknown parameters beta, that is our model. So that is point 2 in this machine learning setup. We have the input data in x, the output data in y, and we have a model which is this input data multiplied with the parameters beta. Now we are making a fit of a polynomial. So this is a very special case. And keep in mind that you're not limited to this kind of models. I mean, you can define whatever kind of model you want. Any questions so far? Is it pretty clear? Okay. So when you look at this, you can generalize it. So you can then think of this matrix as containing other things than just a polynomial. This could be sine or cosine functions. It could be a Fourier series, or it could be other types of functions which you find best fit for the data you have. So this is where your insight kicks in. Now I'm just doing a polynomial because it's pretty easy. So this is in general what you would have here, a matrix like that. So you can rewrite it like that. And now you want to optimize. So we are going to look at an optimization. So I'm just going to scroll down, and I'm not going to take that example. But what we are going to do now is to define a model which we label y tilde. And this y tilde is a notation I will use throughout the lectures. The model is represented by y tilde. Then I want to assess the quality of this model. So what I'm doing then is that I could now take, as was suggested here, the mean square error. This is a very common measure of the error I have. But you could choose the relative or the absolute values as well. So I can rewrite this, and this is something we will discuss a little bit more in the lab tomorrow. You can rewrite this in a more compact way as a transpose of a vector times the vector. And this is something we will remind you about during the lab session this week and also next week. There are some linear algebra elements which we need to refresh, because we're also going to take derivatives of this function. So what we want to do now is to take the derivative of this function c with respect to the parameters beta. And then we want to drive these derivatives to 0. And if that derivative is 0, then we have hopefully a minimum or maximum. This function is a convex function, so it has a minimum. And many of the functions you will encounter, they often are convex functions. And hopefully there's just one well-defined global minimum. But that's the function we want to take the derivative of. And if you then rewrite it in terms of this parameter beta, this is what it looks like. So we have a function now where we have the unknown parameters beta. So we are going to take the derivative of that function with respect to beta. That is the optimization part. Now, the nice thing with linear regression is that we have an analytical expression for this. And one of the things which we will go through during the lab sessions this week is actually the derivation of that analytical expression. So now I'm just going to set it up, and then I want you guys to just go through the notes and think of that, and then we will pick it up again during the lab sessions this week, because the first examples we are going to program deal with the implementation of this. So it's a kind of linear algebra reminder to all of us. So when you do this, you can actually find, and this is what we will discuss a little bit more in detail during the lab sessions, when we take the derivatives of that function. So let me just bring it down here. Just a matter of doing the derivatives. And I invite you to do that. We are going to remind you also of derivatives of matrices and vectors. So these are some technicalities which are good to actually remember. But you can actually set this up, and this is in a function which we want to optimize. So this is actually what we end up with when you take the derivatives. And I multiplied away a minus sign, which you see here, and I've multiplied away 2 over n, which are just constants. And then when you take this equation, we end up with an analytical expression for the unknown parameter. So that means that what you need to do is to take the inverse of the design matrix transposed times itself. And you see the bottleneck here. There's a clear problem. What kind of problems do you see here with linear regression? Yeah?
Taking the inverse.
Exactly. So this is actually one of the bottlenecks of linear regression. And that led in the beginning. So when you want to take the inverse of a matrix, you can cheat. You can actually add on a diagonal in case you have elements which are 0. That will obviously lead to problem with the inverse. But what people did back in the 70s was to add just a number close to 0 so that you could actually invert the matrix. But that is cheating. But that actually led to a reformulation of linear regression in terms of something which is called ridge regression. Has some of you heard of that? That's a method in optimization theory, which has a very interesting mathematical, how to say, and this is an interesting mathematical analysis, which we will discuss in the coming weeks. But linear regression, if you can invert the matrix, you have the analytical expression for the unknown parameter. Then you may ask, hey, where's the machine learning here? I said that this is a kind of low-level machine learning method, and the machine learning is in you learning the unknown parameter beta by this algorithm. So every machine learning algorithm, whether it's a deep learning with neural networks, learns the unknown parameters of your model by a specific recipe. So just keep that in mind. So what you have here is you learning the unknown parameter of a polynomial by a matrix inversion algorithm. So it's pretty straightforward. And many people are actually very disappointed when they see that at the end, we are just trying to optimize a function as a function of given parameters. But the way you do this is different from these methods to neural networks, where you actually let the machine through the algorithm evolve so that you learn the optimal parameters. Whereas here you have an explicit analytical expression, which gives you the unknown parameter. And if you can invert, then you have solved the problem. And this is the y is known, x is known. So everything on the right-hand side is a known quantity. So this is doable if you can invert the matrix. So what we are going to do in the lab sessions is actually to look a little bit more, both today and also on Wednesday. As I said, the sessions are all the same. So it doesn't matter which one you attend. We are going to say a little bit about the mathematics behind these expressions. And then the first exercises deal with you trying to implement this matrix inversion. And with NumPy, you have stable algorithms for inverting the matrices. You will be exposed to linear algebra methods like singular value decomposition. Have you heard of that method, SVD? Excellent. That is the most beautiful algorithm in linear algebra. And that plays an essential role in many machine learning algorithms. So we are going to encounter that one, which is used to calculate the pseudo-inverse, and then many other methods from linear algebra. Okay, I'm going to stop here. Any questions so far? So this is from where we will start our first exercises, and we will discuss some of these technicalities in the lab session. Okay. Any questions from you guys online? Okay, I'm going to shut down and then I will be uploading the video after the lecture here.